So for today, we are going to talk about approximation of integrals. And so leading off here, asking you to set up the integral, which would give the area that's bound by the curve, y equal to sine of x squared, that's shaded below. So this area we could represent as the integral from 0, and because this is the square root, because this is sine of x squared, then its x-intercept is going to be at the square root of pi. So that will be our upper bound. Of the curve sine of x squared dx. Now, geometrically, this integral is very easy to represent as the shaded area under the curve. But algebraically, going through all of our techniques of integration, we don't have any methods that will allow us to integrate this. But it is an important integral. It's used in designing highways. And there's also a lot of other really important integrals. In fact, the vast majority of integrals out there cannot be integrated. And so we need some other technique that will give us an approximation of these integrals. So that's big picture what we'll be doing today. So why do we need to be able to do this? A couple reasons. There's so many functions that we don't know how to anti-differentiate, as I just mentioned, and these are a few of them. We will learn how to do the integral from 0 to 1 of e to the negative x squared dx, that middle one. We'll do that in a couple weeks when we get to sequences and series, but for now, we don't have any way that will allow us to integrate it. Another reason that the approximation of integrals is helpful is that it will allow us to evaluate scientific data that's in the forms of tables and charts. Tables and charts, they are discrete. That means they're not continuous. And if a function is not continuous, then you cannot differentiate it. And so we still would like to be able to pull some of that application of integrals out of the data, but without using an integration, we need some other technique. And so the approximations that we're going to learn today can be scaled up to give a very accurate approximation of data that you find in charts. Okay, so this is going to seem really similar to what we've already done before back in Calc 1. So when we first defined integrals, we defined it as the area under the curve. We would take rectangles, which are nice and easy to find the area of, and then we'd make those rectangles smaller and smaller and add them up, and that gives us the integral. So we could find the approximation. No, that was a definite integral, so then you could find the actual integral that way. But for us, let's start by defining some terminology. So we know that we can represent the area under the curve from a to b of f of x dx. Geometrically, it's this shaded area. So we can break it up into rectangles. I have a lot of slides here. Okay, and A is going to be the start of our domain. B is the end of our domain. We define n as the number of subintervals. So in this case, in our graph, we have n equal to 8 subintervals. And delta x is the width of each of our subintervals. We can find algebraically delta x by taking the difference between our upper bound and our lower bound and dividing by the number of subintervals. And so this is always true. This is how you will find your delta x's. Now, we define x sub I as the right endpoint of the ith subinterval. So if x sub I is the right endpoint of the ith subinterval, that means that x sub 1, a little side note here, all right, let's try this again. All righty. Sorry about that. So this means that x sub 1 is the right endpoint of the first subinterval. And if we know that, then that allows us to also define our bounds a and b in terms of x sub n. It's skipping on me here. There we go. So if x sub 1 is the right endpoint of the first subinterval, then that means the one to the left of it, our a, that's going to be x naught. And then at the end of our domain, we can define b as x sub n. And to generalize, the ith subinterval is just any random subinterval that's going to fall in between our bounds a and b. Now, if x sub I is our right endpoint of the ith subinterval, then x sub I minus 1 is the left endpoint of the ith subinterval. And that's important because it allows us to define the midpoint of the ith subinterval. So we defined the midpoint as x sub I bar. Just by definition, that is what we call each of these. And so we can find the midpoint of the ith subinterval by averaging its two endpoints. So it's 1/2 the left endpoint plus the right endpoint. So x sub I star is just a designated x sub I. So we can just pick an x sub I depending on which rule we want to use to approximate our integrals. And we'll go over several of those different rules today. So now we have all of the terminology we need to define our integral from Calc 1. That's the limit as delta x goes to 0 of f of x sub I star times delta x, where f of x sub I star, that is the height of the subinterval and the width of it is the delta x. So you're just finding the area of this rectangle and you're letting delta x go to 0. So you're making them infinitely thin, you're adding them all up and that gives you the integral. But we can approximate this with just the sum of the rectangles. So this is a finite sum of the area of each of the rectangles. Let's see, the height. Giving us the area of the rectangle. And this sigma, that is a capital letter sigma, if you haven't seen that before. And it just means sum. So we're just summing up the area of all of those rectangles. Think S sigma, S for sum. Somebody once told me that the reason an integral sign is the way it is because it's a stretched out S. I don't know if that's true, but it kind of always stuck with me because we're adding up all the rectangles. Okay. So how do we put this to use? That's all very theoretical, the x sub I star stuff. It starts to sound a little bit scary, but in practice, this should be rather straightforward for you. So there are several different common choices for our x sub I star. And how we choose our x sub I star, that will determine the height of our rectangles. So for example, if we're using the midpoint rule, then the height of each of these rectangles is going to be determined by the midpoint of each of the subintervals. We are wanting to approximate the definite integral from a to b of f of x dx with m sub n. So m means we're using the midpoint rule, and n is the number of subintervals we're going to use. And so we add up the area of each of these rectangles and think, this is the height. Looking at our sketch, if we're just looking at some x sub I interval, then the height, that red so you can see it, then that height is f of x sub I, midpoint, so f of x sub I bar, and then delta x, that's the width of each of our rectangles, which we can find, just to review, that's b minus a over n. So we're adding up all of these rectangles where we're using the height as the midpoint of the interval. And so by definition, we are approximating, make sure you have the approximate sign instead of an equal sign, the definite integral with delta x, and distributing, we're distributing the delta x over all of the heights. That gives us the area of each rectangle. Oh, you guys have to tell me when it does that. Sorry. Make it big for you. Hopefully the Zoom people are still okay. Other common rules that we will use, the right-hand rule. The right-hand rule just means that we are going to use the right endpoint of the subinterval as the height of our rectangle. So looking at the right endpoint of our first rectangle, that would be x sub 1. The right endpoint of the second interval would be x sub 2, and the right endpoint of our very last interval, that would be x sub n. So to find the approximation using our right-hand rule, we would have delta x times f of x sub 1 plus f of x sub 2 plus dot, 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 and then ending with the right endpoint f of x sub n. For the left-hand rule, now we're looking at the left endpoint of each of these rectangles. And so we're using that to determine the height of the first rectangle, the height of the second rectangle. We would start with x sub 0, then x sub 1, x sub 2, and then for the last rectangle, we're determining the height of it using the left endpoint, which would be x sub n minus 1. So filling in for our formula, we start with the left-hand rule, we start with f of x 0, f of x 1, and then we end with f of x sub n minus 1. And while this may seem very conceptual, in practice, it's rather straightforward. So let's do an example. Let's say we want to approximate the integral from 1 to 3 of e to the x squared dx with L sub 4. So the L sub 4, that tells us the rule. We want to use the left-hand rule. With 4 subintervals. Knowing that, we can find our delta x. So delta x, that is equal to our b minus a over n. where b is our upper bound and a is our lower bound on our integral, giving us that delta x is 3 minus 1 over 4, which simplifies to 1/2. If we did a quick sketch, starting at 1, going to 3, and using our left endpoints here. So delta x is 1/2. 1.5 to 2.5 and 3. The height of our first rectangle is determined by f of 1. The height of our second rectangle, we're using f of 2. In fact, I'll write this in as we go. So we're approximating the integral from 1 to 3 of e to the x squared dx, approximating it with L sub 4, and L sub 4 is equal to, we have our delta x out front, and then the height of our first rectangle, that's e sub 1, or if we want e sub 1 squared, plus the height of our second rectangle, that would be e raised to the 1.5 quantity squared. 5 squared plus e to the second power quantity squared plus e to the 2.5 quantity squared. Parentheses maybe make that a little easier to see. And that's where we stop, because for our last rectangle, using the left-hand rule, it has a height of the 2.5, e to the 2.5 squared. And then there's very few times where I will ask you to sub this into your calculator, but this is one of those times where I think it's just a nice check for you to make sure your answer makes sense. And then for us, it makes it just a little bit easier to kind of see that you're on the right page. So this is approximately, and I'm going back to my approximately signs because I am rounding now, 292.40, I just went out 4 decimal places, to 4085. And this is the work you would need to show. So notice that the way I have this written in its unsimplified form, you can tell just by looking at it what values you're using for the endpoints. So when you're doing this for your work, don't do any simplification in your head. Literally just plug whichever endpoints you're using or midpoint into the integrand. And then from there, you can use a graphing calculator or a scientific calculator to find that approximation. You can also use an online integration like Wolfram Alpha or a scientific graphing calculator. You could find what this definite integral is equal to and use that also to check your work to at least see that you're in the same ballpark. So to use the midpoint rule, for example 2, we don't want to have to sketch a graph every time. And so instead of sketching a graph, a number line will be very helpful. It's easier, and especially with the midpoint rule, it helps to show where you're finding your values from. So let's start with we should start with our delta x. Delta x is 6 minus 4 divided by 4, because we have m sub 4 4 subintervals, and that is 1/2. You can write it as 1/2 or 0.5, makes no difference. So for our number line, we're going to start at 4, and we'll go to 6. And making it kind of big just to exaggerate here, knowing that we need 4 subintervals. That also lines up with our delta x of 1/2. But now we're using the midpoint rule. So we want the midpoint of each of these intervals. And so for our first interval, the midpoint's 4.25. For our second interval, the midpoint is 4.75. For the third interval, the midpoint is 5.25. And for our fourth subinterval, the midpoint there is 5.75. So now we're approximating the integral from 4 to 6 of the square root of 1 plus x cubed dx with m sub 4. And m sub 4 is equal to gonna make a little more room here. M sub 4 is equal to our delta x, so that's our 0.5, and then subbing our midpoints directly into the integrand without doing any simplification at all. We have 1 plus 4.25 quantities cubed plus 1, the square root of 1 plus 4.75 cubed plus the square root of 1 plus 5.25 cubed. I thought I could fit it, but I can't. Plus the square root of 1 plus 5.75 quantity cubed. And again, while this is just a tiny bit tedious, think of it as easy points for you because there's very little thought involved. And for me, it shows very clearly how you found your endpoints and which ones you're using. And then sub that in your calculator, and you should get about 22.56. Now, if I'd gotten exactly 22.56, I'd put an equal sign here. But because I had to round, I used the approximately sign. Okay, questions on that one? Yes.
So in what situations would
Okay, so he asked in what situations would I like to see the answer in this form, and in which situations would I like to see the answer in this form? And the answer is always for both. These are the two pieces of work that I would like to see as your full answer. One more rule, and that is the trapezoid rule. So for a trapezoid, if we look at our trapezoids under the curve here, and imagine that we are rotating this trapezoid 90 degrees, then to find the area, that's going to be 1/2 base 1 plus base 2 times height. And so subbing that into our formula, we get that, and simplifying, notice that we have an f of x sub 1 twice. We have an f of x sub 2 times. We have, on the other end, an f of x sub n minus 1 twice. The only things that we don't have in there twice are the endpoints. So we just have this f of x naught in there one time and the f of x of n in there one time. So simplifying, combining like terms, the formula for the trapezoid rule becomes delta x over 2 pulling that 1/2 out. And then that is times, we only have the f of x sub naught, the left endpoint is only in there one time, plus 2 times f of x sub 1, plus 2 times f of x sub 2, plus dot, 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 plus 2 times f of x sub n minus 1, are next to our last subinterval, plus, and then just an f of x naught, f of x sub n, my apologies, as your last height for your subinterval. Okay, so that's your formula for your trapezoid rule. So let's do an example. For example 3, let's start by finding our delta x. Delta x is b minus a, so our upper bound minus our lower bound, divided by our number of subintervals, which is 5. So 2/5, I think it might be a little bit easier if we think of that as 4/10 or 0.4. So making our number line, we're starting at 2, ending at 4, and we will have 5 subintervals in all. One, 2, there we go. Okay. So then if we're starting at 2 and our delta x is 2.4, and our delta x is 0.4, then that gives us endpoints of 2.4, 2.8, 3.2, and 3.6. So subbing this into our formula, we have the integral from 2 to 4 of x cubed dx is approximately t sub 5, which is equal to, we have our delta x, 0.4 over 2, and then that is times, subbing in our left endpoint of 2, we have 2 cubed, plus 2 times 2.4 cubed, plus 2 times 2.8 cubed, plus 2 times 3.2 cubed, plus, always running out of room here, two times 3.6 cubed. And now that we're on our very last endpoint, we don't multiply by 2. In fact, maybe just to be clear, I'll put a 1 in front. 4 cubed. 1 there too. And that's the work that I would want to see. And when you sub that into your calculator, again, we'll get a decimal approximation of 60.48. Questions on that one? Yes. You wanted to know how many significant figures do I want you to use? In these ones, a couple, 2, 3, 4, something like that is fine. Web work, you probably need like 6. Otherwise, for web work, you can just enter your answer in this form and it will take it. Okay, I'm going to skip example 4 for the sake of time, but it is just an example where you are using a table rather than a function for your approximation. So let's talk big picture, and I will post these. So maybe instead of trying to write down everything I say on this page, it might be a little bit easier for you if you just follow along, and then later you can go print off this slide or write down the high points of it. So which techniques are the most accurate? Mostly it's going to be the midpoint rule as the most accurate because the midpoint rule tries to account for the concavity of the curve. So the more curvy the subinterval is, the worse your left-hand and right-hand endpoints will be. So midpoint is generally the one to go to. If you need a more accurate answer, well, we could do more subintervals. That would always give you a better approximation. You could also use a better formula. There is one called Simpson's rule, which uses parabolas to approximate the rectangles or the area under the curve, but we don't cover Simpson's rule, and I mainly just mentioned it to tell you we don't cover it. So when do our approximations give us an overestimate or an underestimate? So let's look at our left-hand rule. And I sketched some random curve and using our left-hand rule here, it looks like on part of the curve, here we're getting an overestimate, and on part of the curve, right here, we're getting an underestimate. And so when we're using our left-hand rule and f of x is decreasing, we get an overestimate. And when, there we go. And when f of x is increasing, then our left-hand rule gives us an underestimate. Now, I don't have these memorized because why waste the brain space? I just sketch a graph, a little curve, and draw a rectangle, and that's all you need. So if you saw something like this on a homework or an exam, this is a good justification right there. Similarly, for the right-hand rule, now just sketching another graph here, noticing that where our function is decreasing, our right-hand rule, where is my right-hand rule? Is giving us an underestimate. Here we have our underestimate, and where, and still we're decreasing, we're still getting an underestimate, and one curve is concave up, the other one is concave down. So the concavity doesn't play into this. It's just whether the curve is increasing or decreasing. So when the curve is decreasing, our right-hand rule gives us an underestimate, and likewise, if you were to draw an increasing curve and use your right-hand rule, you would see that you're getting an overestimate. For the trapezoid rule, though, where does the trapezoid rule give us an overestimate or an underestimate? And in this case, it doesn't matter whether the curve is increasing or decreasing. As you can see here, we have an underestimate and the curve is increasing, and we have an underestimate and the curve is decreasing. So the increasing, decreasing doesn't matter, but what does matter is the concavity. So we have an underestimate when the trapezoid rule, when the function is concave down, and we have an overestimate when the function is concave up. So, and again, don't memorize this, just draw a sketch and it should kind of show you which is which. How can you tell if a curve is increasing or decreasing and its concavity? If it's a really simple curve, something like e to the x or natural log of x or x squared, those you can just sketch. You know those where, it's easy to show where those are increasing and decreasing. For a more complicated curve, you might need to think back to Calc 1, where if the function is increasing, that means its first derivative is positive. And if a function is decreasing, that means its first derivative is negative. So you'd have to find where that first derivative is positive and negative. And similarly for concavity, you would have to find where the second derivative is positive and negative to know where the curve is concave up and concave down. So for more complicated functions, you will need to use that method. Okay. So the big question here is exactly how accurate are our approximations? What affects the size of our error? Thinking our subintervals n. Now, as we have more subintervals, how will that affect our error? I should make it go down. Thank you. Our approximation should be more accurate, and so the error will decrease. On the other hand, b minus a, that's the width of our rectangles. So if we make b minus a bigger, we're making those rectangles wider. And so that means that our approximation is not going to be as good. And so in that case, the error increases. And then k is a measure of our curviness. So think about how far the curve is from like a straight line. And the more curvy your function is, then the greater your error will be. And by definition, we can find k by finding the maximum value of the second, the absolute value of the absolute max of the second derivative on the interval. And that's a mouthful, so I'm going to write it down. This is saying that we can bound k, or we can find our value of k, by finding the absolute value of the absolute max of the second derivative on our interval from a to b. And if you think back to Calc 1, to find the absolute max of a function, you take its derivative, you find any critical numbers, and then you evaluate those critical numbers and the endpoints in your original function. So I'll walk you through that part, but what you really like walk away with is thinking that if we want to find the absolute max of the second derivative, we have to take its derivative. So you're looking at the third derivative to find your critical numbers. But I'm jumping ahead. So let's first talk about how to find the error. The actual error, I'm going to skip for the sake of time. No, I can do this. Okay, so if we wanted to find the actual error, there's only one way to find that exactly. And that is if you know the actual value of the integral. And from that, you subtracted the approximation. So just if we knew that the integral from a to b is equal to 2, and our approximation, we got 1.5, then the actual error would be 0.5, the difference between the two. If you get a positive number back, it means the approximation is an underestimate. If this value is less than 0, that means that your approximation is an overestimate, but we're always going to deal in terms of absolute values, so you don't have to worry about that. The idea is bounding the error. If we know the endpoints and we know n, then we can find an upper limit. We can guarantee that the error will be less than this value. And just like we had talked about on the previous slide, looking at this relationship between the error and k, the width of our intervals, and the number of subintervals. As k increases, it's in the numerator, the error will increase. As b minus a increases, it's in the numerator, the error will increase. And as n increases, as the number of subintervals is greater and greater, since this is in the denominator, it will make your error bound less. So that's a little bit of an idea of where that formula comes from. You don't need to memorize it though. If I am ever asking you to find a bound on the error, I will always give you that formula. I think that's the first time all semester where I said I will give you the formula, but this one I will. Okay, so what can we do with error bounds? And this kind of leads into what kind of questions will you see relating to error bounds. So If you know the number of subintervals, you can bound the error. You can say, I can guarantee the error will be less than this value. If you know that you want the error to be less than some value, we can find how many subintervals we need to make that happen. And then we can also find k if we're given our function on a closed interval. So let's do an example. Let's find an error bound. And in this case, when we're finding error bounds, I will always specify how many decimal places to go to. So here we want to go to 5 decimal places. When we are approximating the integral from 0 to 3 of 2x to the 4th minus 16x cubed plus 20x squared plus 7. And we're going to use the trapezoidal rule when n is 31. And we're given that the absolute value of the second derivative is less than or equal to 56. So let's figure out how that relates to our formula. The second derivative, when we're told that it's less than or equal to 56, that means that our k value is 56. To find our b and our a, we look at our bounds. A is our lower bound, b is our upper bound, and n, well, here is just given to you as 31, or it could say t sub 31, and then you would know to use n equals 31. So you're given the formula. We can bound our error by k times b minus a cubed over 12n squared. So let's sub in our values. This is less than or equal to, k is 56, 3 minus 0, quantity cubed, and that is divided by 12 times 31 squared. And that is approximately some number that I didn't write down, because that's the wrong answer. Anyone have a calculator handy? It's like 0.13111. And then give me a little bit more. 0. 131113424. Great, thank you. So I wrote it out longwise here because I wanted to talk about how we should round this. So if we're going to 5 decimal places, let's look at our 6th decimal place then. So we have 1, 2, 3, 4, 5. Okay, so we're looking at this 3 here. And normally, because 3 is less than 5, we would round down. But let's take a look at what's really going on here. We're trying to find a bound on the error. And let's say we do round down, but let's round way down. Let's round all the way down to 0. If you could pull your mask over your nose, I'd appreciate it. Thank you. So let's say we round all the way down to 0. Can you guarantee me that the error bound is going to be less than 0 when we're approximating this integral with t sub 31? No. So if you can't guarantee it's going to be less than 0, we can't round down. On the other hand, can you guarantee me without any doubt that the error will be less than 100%? Yes. So rounding up, we can confidently guarantee what the error is. And so that means that we should always round up. And that's why I wrote it out in green. It's nice because if you make a mistake, like punching it in your calculator like I did, I can still see that you're rounding it correctly to give you back more partial credit. So this is 0.13112. And if that's not good enough, then we could increase our n. And as we increased our number of intervals n, then we'd be decreasing our error bound. Yes.
So for example, if we had 0.1311104, we'd still round it up. Okay.
Always, yep.
Yeah.
The only time you wouldn't round up is if you had like an exact answer. If you got back 1/2, then you would just leave it as 1/2. Okay. So let's flip this around. Let's say that we know we want our error to be less than 10 to the negative 3. How many subintervals do we need in order to guarantee that? So let's start with our error bound. The size of our error is less than or equal to, our K is 56. Our bounds are still from 3 to 0. And this is divided by 12 n squared. Now, this is the error, and we want that to be less than or equal to 10 to the negative 3. So you want to kind of think about where the inequalities are being placed here. That's probably the biggest mistake I see on these problems, is making your error very large rather than trying to make it very small. So I kind of like to think of it as the formula. This is the approximation on our error, and we want it to be less than or equal to 10 to the negative 3. Okay, so let's cross multiply here. And that will give us 56 times 3 cubed. And let's multiply both sides of this equation by 10 cubed. And we'll leave the 12 in the denominator. And we'll multiply both sides through by n squared. Solving for n, we have that n is greater than or equal to the square root of 56. Actually, we can simplify that down, that fraction there. We can simplify that down to 14 times 3 cubed times 10 cubed, but you don't have to. The square root of all of that. And when you sub that into your calculator, you should get that this is, actually you should show this, is 354.96. Now, n is your number of subintervals, and we are looking for the smallest n. So if we used 354, then there's no guarantee that our error will be less than 10 to the negative 3. So again, we want to make sure that we are rounding up when we're finding our smallest n. And so your final answer should be n equal to, so we're switching to an equal sign, 355. Yes. So 12 is 3 times 4. And so the I canceled out the 3 and the 4 with the 56. Oh, and that should have been a squared because I took out one of the squares. Thank you for pointing that out. It should be a squared here. So I canceled out one of these 3s with one of those 3s, making that a squared. And then 4 goes into 56 14 times. There's still algebra, but you know what? In hindsight, I probably would have just copied that exact same thing down. We still have one more example and a minute and a half. I probably would have just copied this thing down and just made the square root of it. Okay, so always round up and change for your smallest n to an equal sign. Okay. So to find our k value that we were using in A and B, we're looking for the absolute maximum of this second derivative. So in order to do that, and I'll skip a little bit of steps here, you need the second derivative, which is 24x squared minus 96x plus 40. And this is what we want to find the absolute max of. So to do that, we have to find its derivative, which is 48x minus 96. And when you set that equal to 0, that gives you 2. So you take your critical numbers and you take your endpoints and you sub them into the whatever you're trying to find the absolute max of. So we would want f of 0, that is one of our endpoints here. Second derivative of 2, and the second derivative at our other endpoint, which is 3, and it is the absolute value of all of these. So you compute those, and when you do, you would get 40, 56, and 32. Thank you. I get in a hurry, and that's when I make mistakes. I appreciate that. Second derivative. Okay, and so your k, without the absolute value signs, this 56, I believe, is negative, but because of the absolute value signs, it becomes positive 56, and that is your k value. Okay, thank you guys for bearing with me, and I'm just under being over. Have a wonderful day, and I will see you guys back here on Monday.